To start, easy golf, difficult golf. Okay, easy golf. By that I mean same elevation. Okay, so and you could apply this to lots of things, not just golf. But I just picked it because golf is an excellent projectile game. Another sport that I am horrible at, golf. My in-laws always try to get me to play it. Okay, so we're going to have a path that's like this. A rainbow, a parabola. Alright, this is the first time we've dealt with things launched at angles. Okay, now that's the path traveled by the golf ball. Okay, at launch, we're going to draw the velocity vector, which is going to be tangent to that path at that point. Okay, it's going to have some velocity, and it'll be called different things in like textbooks and UT and whatever. I'm going to call it VT or V total. Okay, now let's talk about some other vectors here. These red arrows that I'm drawing are the direction and the magnitude of the velocity at different points. Okay, so how should I draw my velocity vector here? The y velocity is 0, so we're going to have a horizontal velocity, and I'm going to draw it really short. Okay, now here's y. I'm going to go down here, and I'm going to look at the x component. Draw this one dotted. The x component of that velocity does not change. It's the same the whole time. Okay, here's the y component of this velocity. Looks like that. Okay, so what I'm saying is this is the same length as this. Okay, so if this is 10 meters per second, what's this? 10 meters per second. It's the horizontal velocity. Okay, here this is going to be much greater. All right. Okay, then this is one of the reasons why we call this easy golf. Okay. When this thing hits, we're going to have a velocity vector. It's kind of looks like the ball's going to go like in through the ground. Okay, but that's not the path of the ball. That is the vector for the ball at that point. Okay, so this is the same magnitude as VT over here. Okay, it's going to be going the same speed when it hits as when it's launched. Now over here, when we have different elevations, that's not going to be true anymore. Okay, it gets more tricky. All right, still my horizontal component is the same as over here. And my vertical component, that's downward, that is going to be the same but opposite direction. Okay, so this right here I'm going to call VIY. And this over here is V final in the Y direction. Okay, all of these other ones are VX. Okay, now we don't really have a problem to solve here. We're just trying to understand the physics before we do any problems. Okay, question, Nan?
Okay, like I can't tell what symbols you wrote that's all the arrows.
Okay, you want me to zoom in here? Oh, it won't let me zoom because I'm recording. Okay, this is VX.
Okay.
This is V initial
Okay.
in the Y direction. Okay, this is V final in the Y direction. Okay, and these main vectors I'm calling V total, the total velocity. Okay. Okay, so let's kind of zoom in on this one. I'm going to redraw it over here. Try and draw it sort of the same. We're going to call it V total. We're going to call this VX. And we will call this VIY. Okay, now that looks very much like something you have done before. What do you think we're going to end up doing here? Oh my gosh, we're gonna sharpen our trigonometry skills and yes, the Pythagorean theorem. Okay. Now sometimes when I say trigonometry, some people get a little bit scared. Okay. All right, like Halloween scared. Okay. All I'm talking about is this. SOHCAHTOA. Okay, is that difficult?
Yeah.
It's really not. Okay, it's 3 keys. SOHCAHTOA. 3 keys on your calculator. It's really not hard to deal with, guys. Okay, you're not gonna freak out about this, but we might need some review, and that's fine. Okay, we'll review and sharpen our trig skills here. Okay, so over here what I want us to do is we're not going to solve one of these tables, but we're just going to kind of start one. Okay, we'll do our trig in sparkly green. First I need to make up some numbers here. Okay, let's say V total is equal to 60 meters per second. Okay, that has to do with how hard the golfer hit the ball. Okay, and they're hitting it up at a steep angle here. Okay, so this might be like a chipping wedge or a pitching wedge. What are they? Did I get those right? Okay. Again, not really my thing. Okay, let's say this is 75 degrees. That's a pretty steep angle right there. This number right here, V total, can never go into one of your kinematic equations. In fact, we should list that down here. Okay? Never put VT into a kinematic equation. We'll just put into an equation. Okay, so that means all of our equations with acceleration in them. Okay, let me dig out a equation page. All of these you can never put V total into. Okay, and here's why. This equation only deals with velocity in what direction? Horizontal, x direction. These equations only deal with velocity how? Y direction, vertical direction. Okay, we're starting to get to know that. Now, is this in the horizontal direction? There's a component that is, but this is not. Is this in the vertical? No, it's at an angle. There's a component of it that is. So what we're going to have to do is solve for our components. And here's how you do it. Okay? For x, all I'm going to do is Vt cos theta. And for y, all I'm going to do is Vt sine theta. Okay, how I knew to use cosine. It is an adjacent side to the angle. Sine, it's an opposite side to the angle. Okay, question? This is going to be, so let's clarify that. Vx equals. Okay, good question. All right, kind of ran out of room over here, but I'm going to put VIY on this side. Okay, so let's just go ahead and I'm going to just rewrite these down here. Vx equals 60, which is my Vt, times the cosine of 75 degrees. Okay, so we fire up our handy dandy TI-80 whatevers. Okay, 60 cos 75. And we get 15.5.
15? I got 55.
Okay, now, ooh, did I do mistake number 2? Let's see. Mode. Nope, I'm in degrees.
Oh, wait, never mind. That means it's
60 co 75. Okay, punch that in. Should be 15.5. And you notice that it's smaller than 60. The components, both x and y, always have to be smaller than the hypotenuse. If you get a number bigger than the hypotenuse, something's wrong. Okay, so I'm gonna round this to 3 sig figs just for simplicity. On UT, you might want to keep 2 more sig figs. Okay, not round so much. And that's still meters per second. Okay, now down here, common projectile mistakes. Okay, calculators need to be in degrees. Okay, no radians. All right, unless of course your angle is given in radians, which is a pain, and we will never do that. Tim?
We should get to degrees.
How do you do that?
Yeah.
Okay, good question. You hit mode, which is right next to the second key. Hit mode. Okay, and my students back in the day used to think it was really funny to come up and change all my calculators to radians. So I'd be doing a problem and then it'd be wrong and they'd just wait there. And they knew why it was wrong. And then I'd be like, oh, dang, radians. I don't know why I just told you guys that. That was dumb. Okay. All right, degrees. Okay, get the other component. VIY equals okay, if we round that one to sig figs, to 3 sig figs, it comes out to 58.0. Okay, so where do these go in our chart? All right, over here, the horizontal velocity, Vx. Okay, oh, brand new pen. Okay, Vx equals 15.5. And V initial upward, okay, that's what this means, VI initial, and Y means vertical, upward, is equal to a positive 58. And we did round that a little bit, but that's okay. We're not actually going to do a problem here. Okay, now we're not given any other information. So there's not really a problem to solve here. All I want you guys to be able to do here is to understand how to deal with the initial velocity. Okay, that's the first situation. Okay, second situation, projectile with elevation change, difficult golf. Okay, so let's just draw something like this. Let's draw a water trap. Down here maybe we have sand trap. Okay, up here we have the little tee box. Okay, there's the ball, there's the tee. Okay, no longer do we have a flat playing field here. Okay, we're going to have some kind of path, but it's going to pass its initial displacement. Okay, let's say it goes down here, passes the traps, and goes on the green. put a little flag. Okay, now the reason why this is more difficult, the elevation change thing. Up here, all of this that we just learned still applies. Okay, the only thing that is not true anymore is this total velocity vector down here is not going to be equal to this one here. Okay, magnitude-wise. All right, as this thing passes this point, it'll have the same velocity as here. But tell me about the velocity down here. Bigger, smaller? It's going to be bigger. It's going to be more negative. It's going to be bigger in the negative direction because gravity's speeding it up down here. We've still got free fall going on. Okay, Gavin? No, the magnitude is bigger. It's going faster, we would say. On the number line, it would be in the negatives, yes, but it's going to be a bigger value than we start with. Okay, so here's our initial velocity vector. Let's draw it again. It's going to be tangent to the curve. Okay, we would call this VT. We're not going to do all of our trig again. Okay, here at the top, this would be Vx, which does not change the whole time. And down here, we're going to have, it's going to hit kind of like that. I'm going to draw this vector longer. The length you draw your arrows tells a bigger value. Okay, we might call this V final. Okay, and it hits with an angle and stuff. All right, so things we need to know about this. Our change in y. Okay, and I'm gonna call this 0.1, and I'm gonna call this down here 0.2. Change in y is negative. Okay, this right here is 0. Up here, this is positive values for y, and down here, negative values for y. Okay, and we haven't even worked any problems yet with this. We're going to do one example on the back here in a minute. Okay, but this is just some things to be aware of that are different from what we've done. Okay, now other projectile mistakes that we need to be aware of. Okay, these are more just reminders. Acceleration is equal to little g. Okay, we have to know that. V final in the y direction is not 0. Okay, does it look like V final 0 here? No. Okay, but all right, let's think about it. Okay, the ball's gonna go and it's gonna hit the green, and what's it gonna do? It's going to bounce and it's going to roll and it's going to stop. Okay? Now we have a 0 velocity. So V final is always right before it hits. Okay, it's the projectile part. It's not the bouncing, rolling, stopping part. Okay, you got to be careful of that. What else? I think those are the main things that we need to be aware of right here. Okay? Question? Yep, little g is negative 9.8. Unless we're playing golf on the moon. And then little g is negative. Anybody? Anybody?
I want to say 3.6.
You guys will learn this later. Okay, but it's 1.6. I like to throw that up every once in a while just to remind us that little g is not always negative 9.8. Yes, in the future we will deal with that.